सभी डिफरेंशिएबल फंक्शंस कंटिन्यूअस होते हैं. लेट मी राइट दैट. हमने देखा एवरी differentiable function is continuous. और अगर वन डायमेंशनल की बात करें, वन डायमेंशनल सेटिंग में हम पाते हैं एक और फैक्ट जो ट्रू है. इन वन डायमेंशनल सेटिंग, in one dimensional setting, what we have is the following fact. I will write it as 2. क्या सही है कि composition of two differentiable function is again differentiable. Composites of differentiable functions are differentiable. ओके. आज इस फैक्ट को हम हाई डायमेंशनल सेटिंग में स्टडी करेंगे. ओके. जिसे हम चेन रूल का नाम देंगे. लेट मी फर्स्ट give you the precise statement of chain rule, then we will discuss several things. So here is the chain rule statement. Let U be an open subset of Rm and V be an open subset of Rn. Let f be a function from U to Rn and G be a function from V to say Rd. Okay. So our aim is to see differentiability of composite functions. So what is the condition so that we can define composition? So here what we have, so these are functions such that the image of U under F is a subset of V. Then we can talk about composition function. Okay. Okay. Let x be any point in U. So we have these things. Suppose f is differentiable at x. F is differentiable at x and G is differentiable, say at fx. At fx, then the composite function or composition GOF is differentiable at x, and what we have is the derivative of GOF at x is given by derivative of G at fx dot derivative of fx. Okay. So this is how we compute derivative of composite function. So प्रूफ में जाने से पहले हम कुछ रिमार्क्स देख लें. हमने देखा था हमने अभी तक नोशंस कौन कौन से देखे डिफरेंशिएबिलिटी के. एक तो पार्शियल डेरिवेटिव्स हैं और डायरेक्शनल डेरिवेटिव्स हैं. ओके. आप जानते हैं, आपने एग्जांपल्स देखे हैं कि ऐसे भी फंक्शन हैं जिनके किसी एक पॉइंट पर हर एक डायरेक्शन में डायरेक्शनल डेरिवेटिव एग्जिस्ट करते हैं. हर एक डायरेक्शन में डायरेक्शनल डेरिवेटिव एग्जिस्ट करते हैं, लेकिन वह फंक्शन कंटिन्यूअस नहीं है. ओके. तो यहाँ पर भी एक और चेन रूल के रिगार्डिंग एक रिमार्क हम देखते हैं which involves directional derivative. Remark 7. uh, the notion of directional derivative does not follow the chain rule. इसका क्या मीनिंग है? इसका मीनिंग होगा कि डायरेक्शनल डेरिवेटिव एक वैलिड एक्सटेंशन या वैलिड जनरलाइजेशन डिफरेंशियबिलिटी का नहीं है। हम जब डिफरेंशियबिलिटी के करेक्ट जनरलाइजेशन या करेक्ट नोशन को ढूंढ रहे थे, हमने यह बात बोली थी कि जो भी नोशन करेक्ट नोशन होगा डिफरेंशियबिलिटी का, वह नंबर वन कंटिन्यूटी को देगा, नंबर सेकंड वह नोशन चेन रूल फॉलो करेगा। ओके, सो here I'll so for this what I'll do, I'll give you an example which shows that this notion of directional derivative does not follow the chain rule. Okay, good. So here is one example. हम दो फंक्शंस लेते हैं g और f. So suppose g be a function from R2 to R2. Okay, कैसे डिफाइन है? g is defined as xy maps to x comma y plus x square. So this is for all x y in R2, and we have another function f which is defined from R2 to R. कैसे डिफाइंड है? xy maps to x square y divided by x4 plus y square if xy non-zero. Okay, and 0 if xy is 0. Then our aim is to show first what we will show. We will show that all the directional derivative of f and g exist. Okay, so here is claim. So first claim is the directional derivatives of f and g exist everywhere. Okay, and there exists so another thing, but there exists a direction, means there exists a non-zero vector such that uh, FOG dash at 0u does not exist. Okay, so we will find a direction where the directional derivative of this composite function does not exist. So first let me okay, so here define or set h equal to FOG. So our aim is to see h dash 0u does not exist. Okay. So first what we will do, we will show that directional derivative of g exists. Okay. For this what we will choose a direction which is non-zero vector. Choose a direction which is a non-zero vector u, and take an arbitrary point a1 a2, and assume that a is non-zero. Or So let me take a equal to even a2. Then first I'll show that g dash au exists. Okay, what is g dash au? This by definition this is limit t goes to 0, t goes to 0, g of a plus t u minus g a divided by t. Okay, so let me write it. Limit t goes to 0. What is g a plus t? Okay, so this is 1 by t. So how did we define g? So this is x comma y plus x squared. So let me write it. So this is g a1 plus tu1 comma a2 plus tu2 minus g a1 comma a2. Okay, and what is g of xy? G of xy is this x comma y plus x square. So here we have limit t goes to 0, 1 by t. So this is a1 plus tu1 comma a2 plus tu2 plus a1 plus tu1 square. Okay. This is one, and second a1 comma a2 plus a1 square. So you may easily compute it, and you will find this is nothing but this is u1 comma u2 plus 2a1 u1. Okay, verify this. So this means in all directions the directional derivative of g exists. Okay, so for g, now we consider f, and we will show that directional derivative of f in each direction exists. Okay, now okay, so first let me take a equal to 0, means a equal to a1 a2, and this is 0 0, and u equal to u1 comma u2, that is non-zero. What is f dash 0 u? Again, f dash 0 u is limit t goes to 0, f0 plus tu. This means this is tu1 comma tu2 minus f0 divided by t. So by definition of f, so definition of f is this: xy goes to x square y upon x4 plus y square. Okay, so this is limit t goes to 0. This would be t square into t square u1 square t u2, means this is t cube u1 square u2 divided by 4 times. Okay, t4 u1 4 plus t square u2 square. Okay, into 1. So f0 0 is 0 into 1 by t. You can now verify that this is 0 if u2 is 0, and this is u1 square by u2 if u2 non-zero. Okay, so verify this. Correct? Now, what we'll do, we assume now, or let a be non-zero. So here we have, in this part, what we have shown, directional derivative of f at point 0 in each direction exists. Directional derivative in each direction exists at the point 0. Now we will take a, b, any arbitrary point. Okay. So what is f dash au? This is again by definition limit t goes to 0, say 1 by t. So this would be a1 plus t u1 square, a2 plus t u2 divided by 4. Okay, so it's power 4 plus power 2 minus a1 square, a2, a1 4 plus a2 square. Okay. So now verify that this limit is uh, okay. So verify that this limit is a1 4 plus a2 square, a1 square, au2 plus 2 a1 a2 u1 minus a1 square a2 4 a1 cube u1 plus 2 u2 divide by a1 4 plus a2 square whole square. This means a directional derivative of f in each direction at any point, okay, exists. So what is uh, h? H was fog. So this means what is hxy? Hxy is f of gxy. Okay. What is gxy? Gxy is x comma y plus x square. And what is it? This is this is 0 if xy is 0, and this is x square y plus x square divided by x4 plus y plus x square whole square if xy non-zero. Now we will find a vector, non-zero vector, such that at h dash 0 u does not exist. Okay, so what is h dash 0 u? Directional derivative of h in the direction u at the point 0. By definition, this is limit t goes to 0, h tu minus h0 by t. Okay, so this is nothing but limit t goes to 0, 1 by t. So t u1 square, t u2 plus t u1 square divided by t u1 4 plus t u2 plus t square u1 square whole square. Okay, so verify that this is equal to u1 square by u2 if u2 non-zero and it does not exist if u2 is 0. This means h dash 0 u does not exist along the x-axis. Okay, this means the notion of directional derivative does not satisfy the chain rule. Correct? Okay, before going to proof of chain rule, let me solve some exercises. Okay, or so here is an exercise for you. So question. Let f be a function from R2 to R3 and g be a function from R3 to R2 given by fx equal to e2x1 plus x2 3x2 minus cos x1 comma x1 square plus x2 plus 2. Okay, and g is defined by so here what I'll so here I should write uh, fx1 comma x2. Okay, fx1 comma x2. So here g y1 comma y2 comma y3. This is 3y1 plus 2y2 plus y3 square, y1 square minus y3 plus 1. Okay, so find df0 where fx equal to g of fx. Okay, so this is a function from R2 to R2. Okay, so how do we do this? So this is very easy. So let me compute this for you. What is df0? By chain rule, df0 is d of g of f0, okay, and multiplied by d of f at 0. This is chain by chain rule. This is by chain rule. Okay, what is f0? f0 means f00. That is, so you see this is e to the power 0 1 uh, 0 and cos 0 1, so it is minus 1 0 0 2. Okay, so this is 1 minus 1 2. What is d g first dg y1 y2 y3, okay, or dgy? What is dgy? Dgy by definition this is, so you see this g is a function from R3 to R2. Okay, the Jacobian matrix will be of order 2 cross 3. Okay, 2 cross 3. So it would be del g1 by del y1. Okay, so with respect to first coordinate, del g1 by del y2, del g1 by del y3, second del g2 by del y1, del g2 by del y2, del g2 by del y3. So compute this. What would you get? And so compute it. So here is G1, this is G1. So this is 3, 2, 2y3. Correct? This is G2, 2y1, 0, minus 1. So this is dgy. So what is dg of f0? F0 is 1 minus 1, 2. This is 3, 2 and 2 to the 4, 2 into 1, 2, 0 minus 1. This is dg f0. Okay. Now we need df0. What is df? What is df x1 x2? This is del f1 by del x1, del f1 by del x2, del f2 by del x1, del f2 by del x2, del f3 by del x1, del f3 by del x2. Okay. So here is f1 2e2x1 plus x2. So this is f1. Okay. So what we will get 2e2x1 plus x2 and e2x1 plus x2. What is f2? F2 is this and f3 is this. F2 is minus sine minus minus plus sine x1 and 3. And lastly, 2x1. Okay, this is 2x1 comma 1. So what this implies? What is this? This is 2 1 0 3 0 1. So now compute df0 equal to dg 1 minus 1 2 dot df 0 0. 3 2 1 2 0 minus 1 2 1 0 3 0 1. Now compute it and you will get this is 6 13 4. Okay, this is how you compute derivative of composite functions using chain rule. Okay, so in next lecture I will prove I will give a proof of chain rule. Thank you.